Fluids in motion. This is a syringe filled with water, and as I push the plunger in, the water squirts out the end. I want you to watch the end of the plunger and the end of the water. Notice that the water is moving faster than the plunger is, and that's because the diameter over on this side is larger than the diameter on this side. What has to be true for this is the volume of water that's going through here has to be constant. The volume that I'm pushing here has to equal the volume that's coming out there. Now, of course, it's happening over the same amount of time. Volume divided by time is called the flow rate. So this is the flow of water moving through here. And that flow rate has to be constant everywhere within your cylinder or whatever's shooting the water out. Now I know volume is area times distance, so the flow rate is going to be the area times distance divided by the time. And distance divided by time is velocity. So this is another way of calculating the flow rate, A times V, and that flow rate has to stay constant. So this is the continuity equation, that the flow rate, A times V, is the same anywhere through your pipe. That's because this volume has to equal this volume, the same volume in the same amount of time. So if we have a small area, it has to be going faster. If we have a large area, it has to be going slower. The fluid speed is greater where the area is smaller. That's what's happening when you're putting your thumb over a garden hose. You're making a smaller area for the opening, and that means the water is going to be going faster at that point. Next topic is Bernoulli's equation. I'm not going to have you memorize the entire equation. We'll just have to remember half of it, because the other half's exactly the same. Bernoulli's equation says that these three terms added together have to stay constant. These terms look sort of familiar. That middle term is actually kinetic energy divided by the volume, and the last term is the potential energy divided by the volume. So the Bernoulli's equation is actually conservation of energy. Bernoulli's principle says that the pressure in a fluid decreases as its velocity increases. So looking at the drawing here, I have a large diameter here going to a small diameter. That makes the velocity go faster. And Bernoulli's principle is saying at this part where it's going faster, it actually has a lower pressure. It's kind of backwards from what you'd expect. If you think of a garden hose, the water's coming out faster, but it actually has a lower pressure than it does inside the hose. Common example of Bernoulli's principle is a perfume bottle. The way the perfume bottle works, as we're squeezing it, we're making the air go faster on the top. Faster moving air makes a lower pressure, and just like sucking on a straw, creating a lower pressure inside the straw will draw the fluid up to the top. And then when you squeeze again, that fluid hits the fast moving air, and then we get the spray coming out. An aerosol can works in a similar way, but instead of pumping it, you're just releasing compressed air that's inside of there. Bernoulli's principle is also used to explain how an airplane wing works. Airplanes fly because of the shape of the wing, and this shape causes the air to move faster on the top side of the wing than it does on the bottom side. If the air is moving faster, we're going to get a lower pressure on the top, and that creates a higher pressure on the bottom. And if we have a difference in pressure, that means we have an upwards force or a buoyant force pushing the wing upwards. This isn't exactly everything that's happening on the wing, but it's basically what they explain in most of the textbooks. We'll talk about other ways to explain this later on. This is the problem that we need to be able to solve for the AP test. It is using Bernoulli's principle. Whenever we have a fluid in motion, you have to use the Bernoulli equations. And we will be using the full equation. The left side of the equation is representing the top of our container, and the right side of the equation is representing the spigot where the water is shooting out. Now these two P's in this problem are representing the atmospheric pressure, and that pressure is the same at top and bottom, so on our equation that part is going to cancel out. And for my kinetic energy over here at the top, we're going to assume that the speed of the water lowering at the top here is very small compared to the speed of the water coming shooting out of here. So small that it's going to be negligible in solving the problem. So the velocity at the top is next to 0, so that energy is next to 0. So the last three terms we're going to combine to figure out what is the velocity down at the bottom. Notice that there's a density in each one of those. Those are all the same density of water, so they will divide out. And then solving the last one, I'll subtract this term, multiply by 2, and square root. You may recognize this equation. This is the same equation that we used for a roller coaster, where we have HA is the height of the top hill, and then HB would be like the height of the second hill, and you're trying to find what is the speed at the top of the second hill. When you're solving one of these problems on the AP test, you are not allowed to pop up with some equation like this. You have to show where it comes from. And for fluids in motion problem, it's coming from Bernoulli's equation, so you have to go through this whole process. End of notes.